Imagine teaching a child every word in every book ever written, then asking them to predict the next word in a sentence. What would emerge is not just the capacity to parrot back information, but to generate something resembling thought. This, in essence, is the work of large language models, or LLMs. They are the mathematical prodigies of artificial intelligence, wielding probabilities like poets with metaphors. Large language models have swiftly integrated into nearly every aspect of our lives, from suggesting the next phrase in a text message to assisting in medical diagnostics and powering customer service chatbots. They are everywhere. These models write emails, code software, generate art, and even compose music. Their influence extends to education, research, and entertainment, fundamentally reshaping how humans and machines interact. Yet, as omnipresent as they are, the workings of LLMs remain enigmatic to most. So, how do they achieve this extraordinary feat? Mathematics is the invisible backbone of these thinking machines. Through techniques rooted in linear algebra, probability, and calculus, LLMs interpret, generate, and even reason with language. They've learned to encode not just the structure of words, but their meanings, relationships, and subtleties. A feat that bridges the chasm between syntax and semantics. However, LLMs remain largely black boxes. Their decisions can often seem mysterious, but understanding the mathematics behind these models helps illuminate their inner workings. By dissecting the algorithms and equations that drive them, we can better grasp their capabilities and limitations, moving one step closer to demystifying their operations. And yet, as remarkable as they are, LLMs don't truly understand. They excel not through cognition, but through colossal computation. Their genius lies in their algorithms, and their story is one of human ingenuity, harnessing the power of numbers to model something profoundly human, language itself. In this show, we take you on a fascinating journey into behind the scenes of the large language models, uncovering the mathematical foundations, innovative breakthroughs, and ethical considerations behind their development. From understanding probabilities and tokenization to exploring the intricacies of transformers and fine-tuning, we'll go into the mathematics to design an LLM. Along the way, we'll examine the deeper questions these models raise about intelligence, creativity, and the role of technology in shaping our future. The story of LLMs begins decades ago, in a world far less computationally advanced. In 1948, Claude Shannon, a mathematician at Bell Labs, introduced a revolutionary concept: information theory. Shannon posited that language could be seen as a sequence of probabilistic events, where each word depends on the one before it. He even outlined ways to simulate text using random processes, a startling glimpse into the probabilistic heart of modern language models. Shannon's ideas laid the foundation for computational linguistics, a field that sought to mathematically understand human language. Decades later, researchers like Joseph Weizenbaum expanded these ideas with systems like ELIZA, the 1960s chatbot that mimicked human conversation through simple pattern matching. Yet ELIZA lacked something fundamental: an understanding of context. It could reply to questions, but it couldn't predict what might come next. Today's LLMs, however, have cracked this challenge wide open. Take a sentence like, "The sun sets in the ... and an LLM might predict west, not through intuition, but by calculating the statistical likelihood based on billions of prior examples. This statistical dance is powered by a groundbreaking architecture, the transformer. Introduced in 2017, transformers revolutionize the field, enabling machines to grasp context at an unprecedented scale. Have you ever typed a message on your phone and watched as it suggested the next word you might want to use? Perhaps it predicted meeting after scheduled or birthday after happy. This simple act of autocomplete reflects one of the most profound innovations in artificial intelligence: the ability to predict what comes next. It's a feature so seamless that we barely notice it, yet it is built on a bedrock of mathematical probability that once reshaped how computers process human language. At the heart of these predictive systems lies the idea of probability, the mathematical science of predicting outcomes based on patterns. Early language models relied on a statistical method known as n-grams, which broke down text into small sequences of words. If you've ever heard the phrase bigram or trigram, you're hearing the echoes of this era. In an n-gram model, predicting the next word is as simple as looking at the most common word combinations in a dataset. For example, if I am often follows who, then the model might predict I am when you type who. The origins of n-gram models trace back to the 1980s, when researchers began applying them to tasks like speech recognition. Imagine trying to transcribe spoken words into text. Early systems relied on probabilities to guess the most likely sequence of words a speaker intended to say. It was groundbreaking for its time, but it also revealed the limitations of fixed probabilities. Words were treated as isolated fragments, and models struggled when the context of a conversation spanned more than a few words. At its core, an n-gram model uses probability distributions to determine the likelihood of one word following another. Each word depends only on the word that came before it. While this approach is computationally efficient, it reduces language to a simple chain of probabilities. It cannot capture the deeper connections between words, ideas, or emotions that make human language so rich. Yet, n-gram models were foundational. They paved the way for modern LLMs by proving that language could be systematically analyzed and modeled using mathematical principles. These early systems provided the crucial stepping stones that allowed later innovations to flourish. Fast forward to today, and we have models like GPT-4 which are fundamentally different. While n-gram models might consider only 2 or 3 words at a time, large language models evaluate the entire context of a sentence, paragraph, or even a conversation. Instead of relying solely on fixed probabilities, they use neural networks to assign meaning to words and relationships between them. This is achieved through embeddings, mathematical representations that place words into a high-dimensional space where their meanings can be compared and contrasted. For instance, an n-gram model might predict the word bank after river based purely on frequency, but an LLM understands that bank in this context refers to a financial institution, not a riverbank. This leap from rigid probabilities to contextual understanding is what allows LLMs to generate coherent essays, craft poetry, and even hold conversations. It's a transition from statistical mimicry to something that feels almost intuitive. But as powerful as probabilities are, they alone couldn't capture the full complexity of language. To truly unlock the potential of LLMs, another innovation was needed: tokenization, the process of breaking down text into fundamental units that machines can interpret. Probability at the foundation of predictive text, the backbone of how large language models operate. But for these models to process language, they need to break it into digestible pieces. This brings us to tokenization, the essential first step in the journey from raw text to machine understanding. Imagine encountering the word unbelievable. For a language model, this word isn't just a single entity. It might be split into three components: un, believe, and able. Why? Because breaking it down allows the model to process and understand not just the full word, but also the building blocks that form it. This process, known as tokenization, enables models to navigate the complexities of language with precision and efficiency. Tokenization isn't always straightforward. Consider languages like Japanese, which lack spaces between words, or scripts that mix characters from different systems, such as English words embedded in Chinese sentences. For these cases, tokenization requires algorithms capable of handling linguistic diversity and ambiguity. One powerful method for tokenization is byte pair encoding, or BPE. At its core, BPE operates like a puzzle solver. It starts with individual characters and repeatedly merges the most frequent pairs into larger units. Over time, this process builds an efficient representation of the text, striking a balance between breaking language into manageable chunks and preserving meaning. Why does this matter? Let's take unbelievable again. A model using BPE might recognize that un and able are common prefixes and suffixes, while believe captures the root meaning. By identifying these patterns, the model optimizes its understanding without needing to memorize every possible word in existence. It's a delicate dance, one that balances efficiency and the richness of meaning. Tokenization is just the beginning. Once the text is tokenized, how does a model transform these tokens into something it can compute with? That's where the concept of embeddings comes into play. These mathematical representations unlock the door to the high-dimensional space where meaning begins to take shape. If tokenization is like breaking language into manageable building blocks, embeddings are what give those blocks their shape and meaning. Imagine arranging pieces of a jigsaw puzzle. Each token is a piece, and embeddings help us see how they fit together within the larger picture. This process allows machines to understand not just the surface structure of language, but also its deeper relationships. The journey toward embeddings begins with the question: how can machines represent the meaning of words mathematically? Before embeddings, language models relied on rigid rules and statistical counts, which struggled to capture the fluid, nuanced nature of human language. Then, in 2013, Tomasz Mikolov and his team introduced Word2Vec, a breakthrough that fundamentally changed the field. Word2Vec did something extraordinary. It transformed words into vectors, points in a mathematical space, where relationships between words could be visualized and computed. For example, in this space, if you subtract the vector for man from king and add the vector for woman, you arrive startlingly close to queen. This algebra of meaning was revolutionary, offering a glimpse into how machines could interpret the relationships between words. To picture this, imagine a 300-dimensional graph where each word is a point. Words with similar meanings cluster together. Dog, kitten, and pet might be neighbors, while unrelated terms like pencil and loudspeaker would sit far apart. These clusters reveal the connections that form the bedrock of semantic understanding. But embedding isn't just about proximity. Consider the word bank. Is it a river bank or a financial institution? In vector space, these meanings are distinct. Machine learning models rely on context to place words in the correct cluster. For instance, deposit might pull bank toward its financial meaning, while water nudges it toward its geographical sense. The mathematics of embeddings leverages tools like cosine similarity to determine how closely two vectors align. Think of cosine similarity as the angle between two arrows in space. The smaller the angle, the more similar the meanings of the words. This technique helps models not just understand words, but also grasp their relationships within a sentence or phrase, a critical step in language comprehension. Embeddings revolutionized natural language processing, but they also had limitations. They captured individual word meanings well, but struggled to understand sequences or context beyond individual words. To address this, researchers turned to a new paradigm, transformers and attention mechanisms, which enable models to analyze and understand sequences as a whole. If embeddings laid the foundation for understanding words in isolation, transformers revolutionized how machines understand language in context. At the heart of this transformation is a simple yet profound idea: attention. With attention mechanisms, models can analyze words not just as individual entities, but in relation to everything else in a sentence. The breakthrough came in 2017 with a research paper that would change artificial intelligence forever. Titled, "Attention is All You Need," this work by Vaswani and colleagues introduced the transformer architecture. Its innovation was as bold as its title, to discard older sequential methods and instead let models pay attention to all parts of a sentence simultaneously. To understand why this was so revolutionary, consider the challenge of pronoun ambiguity. Take the sentence, "John saw Bob, he waved." Who waved? Traditional models struggled with such questions because they processed words in a fixed order. Transformers, however, use attention to look at every word and determine the relationships between them. In this case, the model learns from context, perhaps by noticing prior patterns, to correctly infer whether he referred to John or Bob. So, how does this attention mechanism work? At its core is a process called self-attention, where each word in a sentence evaluates its relevance to every other word. Imagine reading a sentence and underlining the words most related to a specific term. Self-attention automates this, assigning weight to indicate the importance of one word to another. The mathematics behind it is elegant. At the heart of self-attention is a formula involving queries, keys, and values, concepts borrowed from information retrieval. Queries represent the word in focus, keys help identify relevant words, and values hold the associated information. Together, they create attention scores, which determine how much influence one word has over another. But there's a challenge. Sentences can be long, and without adjustments, attention calculations can become overwhelming. This is where scaling comes in. By dividing attention scores by the square root of the key dimensions, the model ensures stable computations, avoiding extremes that could distort its understanding. And transformers don't stop at one attention mechanism. They use multi-head attention, running multiple attention operations in parallel. Each head focuses on different relationships within the sentence. For example, one head might track subject-verb agreement, while another links pronouns to their antecedents. Together, these heads provide a richer understanding of context. If transformers excel at focusing on context, they still face a fundamental challenge: understanding the order of words. Unlike humans, these models don't inherently know that word order shapes meaning. Take the sentences, "The cat chased the mouse," and "The mouse chased the cat." The words are the same, but the meaning flips entirely based on their sequence. So how do transformers learn the rhythm of language? Enter positional encoding, a technique that helps transformers grasp the sequence of words in a sentence. Think of it as assigning each word a unique rhythm, like a beat in a song. Each beat, or position, provides the model with a sense of structure, helping it understand not just the words themselves, but how they relate to one another in time. Let's break this down with an example. Imagine our earlier sentence, "The cat chased the mouse." Positional encoding assigns each word a mathematical signature based on its position in the sentence. These signatures aren't random. They're crafted using sinusoidal functions, wave-like patterns that repeat predictably. This predictability allows the model to understand relationships between words, even if the sentence length changes. But why sinusoidal functions? They have a unique property. They encode relative distances between words. For example, the distance between "the" and "cat" remains clear, even if we add words to the sentence. This consistency ensures that the model maintains an understanding of sequence regardless of input length. Of course, sinusoidal encoding isn't the only approach. Some models use learnable positional embeddings, where the model itself determines the best way to represent positions during training. While this offers flexibility, it requires more data and computational power to learn effectively. Positional encoding solves a critical piece of the puzzle, giving transformers the ability to interpret order. But understanding order is only part of the challenge. To truly learn, these models must also adapt, refining their knowledge through trial and error. Next, we explore the mechanisms that enable transformers to improve themselves, taking us deeper into the world of optimization and learning. Positional encoding gave transformers the ability to understand the sequence of words. But how do these models improve themselves? How do they refine their knowledge to minimize mistakes and maximize accuracy? The answer lies in a process inspired by one of nature's most fundamental principles: learning through error. Imagine you're navigating down a mountain in dense fog. You can't see the peak or the valley, but you know your goal is to find the lowest point. You take a step, feel the slope, and adjust your direction based on whether you're heading downhill or uphill. This is the essence of gradient descent, the process that allows models to learn and improve. At the heart of this process is the concept of a cost function. Think of it as a map that measures how wrong a model's predictions are. The higher the cost, the farther the model is from the correct answer. Gradient descent is the method models use to adjust their parameters, their internal settings, to reduce this cost. This process became practical thanks to a revolutionary idea from the 1980s, backpropagation. Geoffrey Hinton and his colleagues developed a way for models to calculate how much each parameter contributed to an error, and to use this information to improve. Backpropagation was the breakthrough that made modern neural networks possible. The mathematics of gradient descent is deceptively simple. It uses calculus to compute the slope of the cost function, the gradient, and adjusts parameters in the direction that reduces error. But simplicity doesn't mean perfection. Early models faced a major hurdle: vanishing gradients. As networks grew deeper, the gradients often became too small to make meaningful updates, stalling learning. Researchers tackled this problem with innovations like the Adam optimizer. Let's return to our foggy mountain analogy. Imagine that each step you take is informed not just by the immediate slope, but also by your past steps. If you've been stepping in the wrong direction repeatedly, Adam adjusts your stride to correct the mistake. Similarly, if you've been making consistent progress, it might encourage larger steps to speed things up. This adaptability makes Adam an efficient and robust tool for optimization. These techniques, gradient descent, backpropagation, and optimizers like Adam, are some of the common methods we discuss in this show. However, cutting-edge models often combine these with other advanced or proprietary algorithms, pushing the boundaries of what AI can achieve. Gradient descent and backpropagation form the backbone of how models learn. They take the vast complexity of neural networks and make training possible, step by step. But as these systems grow, they must navigate another crucial challenge: uncertainty. How do models balance randomness and determinism to handle ambiguity? Enter entropy, a concept that governs how large language models make sense of an unpredictable world. In the intricate world of large language models, understanding and learning are only part of the story. Equally vital is the ability to navigate the unknown. How does a model decide between certainty and exploration, between sticking to the predictable and venturing into the creative? The answer lies in entropy, a concept as fundamental to AI as it is to the universe itself. At its core, entropy is a measure of uncertainty. In the context of large language models, it determines how unpredictable a model's outputs are. Imagine asking a model to complete the sentence, "The cat sat on the..." A low entropy response might predict, "Matter safe," common answer. A high entropy response might venture into the unexpected, "Moon," or "Volcano." This balance between randomness and determinism is controlled by the temperature setting. High temperatures increase entropy, encouraging the model to take creative leaps. Low temperatures reduce entropy, favoring predictable, coherent answers. For example, in writing a poem, a higher temperature might inspire inventive metaphors, while a lower temperature ensures rhyme and structure remain intact. But why is entropy important? In practical applications, it allows models to adapt to the task at hand. A customer service chatbot might rely on low entropy responses to maintain professionalism, while a story generator might embrace high entropy to produce unexpected twists. The mathematics of entropy originates in Claude Shannon's information theory. Shannon defined entropy as the average uncertainty in a set of possible outcomes. In LLMs, this translates to a model's ability to assign probabilities to different outputs. The higher the entropy, the more spread out those probabilities are. A sign of creative potential, but also unpredictability. Managing entropy is not without challenges. Too much randomness can make outputs incoherent, while too little stifles creativity. This delicate balance is one of the reasons why fine-tuning models for specific tasks is both an art and a science. As models scale, their capacity to manage uncertainty improves, unlocking emergent behaviors, unexpected abilities that arise not from explicit programming, but from the sheer complexity of their design. These emergent capabilities often redefine our understanding of what AI can achieve. If entropy allows models to navigate uncertainty, scaling unlocks their true potential. The phrase, "bigger is better," might sound simplistic, but in the world of large language models, it often holds true. Scaling in parameters, data, and compute, has proven to be the key to unlocking capabilities we once thought impossible. OpenAI's GPT-4, currently one of the most advanced LLM, demonstrates the power of scale with its more than 1 trillion parameters. But what exactly is a parameter? Simply put, it's a weight or value within the neural network that helps the model make decisions. For example, think of a parameter as a dial on a massive control panel. Each dial adjusts how much importance the model gives to a specific input when making predictions. The more dials, the more precise and nuanced the model's responses can be. Let's take an example. Imagine teaching someone to identify animals from blurred photos. A small model with few parameters might only distinguish between cats and dogs. As the parameters increase, the model can identify breeds, notice subtle patterns, and even predict the environment of the animal in the photo. This ability to process finer details is why performance improves as models scale. Yet scaling isn't without its challenges. Beyond a certain point, diminishing returns set in. Doubling the parameters of a model doesn't necessarily double its performance. For example, while increasing from 1 billion to 10 billion parameters might yield significant gains, moving from 100 billion to 200 billion might bring only marginal improvements. And the cost of training these models grows exponentially, requiring enormous computational resources and energy. This brings us to an intriguing question. How big is too big? While GPT-4 has already set remarkable benchmarks, speculation about GPT-5 looms large. Could it have trillions of parameters? Or might researchers find more efficient paths to innovation that don't rely solely on scale? The answers remain as elusive as they are exciting. Scaling unlocks extraordinary potential, but it also forces us to confront critical challenges, balancing efficiency with complexity and understanding how far scale alone can take us. From here we turn to another essential question. How do we ensure these increasingly massive models remain flexible, reliable, and robust, avoiding the pitfalls of overfitting while maximizing their potential? Scaling large language models to massive sizes unlocks incredible capabilities, but it comes with a risk. Overfitting. When a model memorizes data rather than learning from it, it loses the ability to generalize, becoming rigid and unreliable. How do we prevent this? The answer lies in a set of techniques collectively known as regularization. Think of a student preparing for an exam. If they only memorize answers from practice tests, they may excel at repeating those exact answers, but struggle with new questions on the same topic. Regularization ensures the student learns the underlying concepts, not just the specifics, enabling them to apply their knowledge in diverse situations. One of the simplest and most effective regularization techniques is dropout. During training, dropout temporarily disables random neurons in the network. This forces the model to learn more robust patterns by preventing it from relying too heavily on specific pathways. It's like training a team to play soccer by occasionally removing key players, ensuring that every member can adapt and perform under pressure. Another essential technique is weight decay. Think of it as a form of discipline for the model's parameters, discouraging them from becoming excessively large. By adding a penalty to the cost function, weight decay ensures that the model maintains balance, avoiding overconfidence in any single pattern. Layer normalization and batch normalization bring stability to the learning process. Layer normalization ensures that the output of each neuron remains balanced, like adjusting the volume for clarity in a group conversation. Batch normalization takes this a step further by balancing inputs across multiple training examples, speeding up learning and making the model more resilient to noisy data. Together they keep the training process smooth and consistent, even as complexity grows. These techniques work in tandem with data augmentation, where the training data is modified to simulate a wider range of scenarios. For example, images might be flipped or rotated, while text datasets could include paraphrased sentences. This diversity exposes the model to a broader spectrum of possibilities, enhancing its adaptability. Regularization techniques don't just prevent overfitting, they enable models to thrive in unpredictable environments. They transform rigid systems into flexible tools, capable of navigating the complexities of real-world applications. But, as we refine these techniques, we face a new challenge. Equipping models to handle not just vast datasets, but also long-term dependencies and memory. How do we ensure that language models retain context over extended sequences without losing focus or coherence? That's the next frontier, and it's where our story takes us next. Regularization ensures that models can generalize and adapt, but adaptability is only part of the equation. Language itself demands memory, the ability to retain context over extended sequences. How does a model keep track of what came before, ensuring coherence and relevance, even in lengthy conversations or documents? This is the challenge of memory in large language models. Think about reading a novel. To understand the climax in the final chapter, you need to recall details from earlier, a character's backstory, a pivotal event, or a subtle clue. Similarly, language models must remember and weave together context to generate meaningful responses. Without memory, even the most advanced models risk losing their way in long or complex tasks. The architecture of most models limits their memory to a fixed context window, often just a few thousand tokens. Beyond this limit, earlier information fades, like trying to recall a distant memory without notes. Innovations like sliding windows and memory-augmented transformers aim to extend this horizon, enabling models to revisit earlier parts of a conversation or document without starting from scratch. Persistent memory mechanisms go even further. Unlike sliding windows that revisit context incrementally, persistent memory enables models to retain critical information across tasks or sessions. It's akin to keeping a detailed journal that you can reference instantly, ensuring continuity and depth, even in long-term interactions. Looking ahead, researchers are exploring models with infinite or dynamic memory capacities. These systems could integrate external databases or cloud storage, allowing them to hold vast amounts of information. Imagine a model that remembers not just one conversation, but the entirety of your interactions over years, adapting and growing with you. But memory isn't just about technical implementation. It's a critical component of understanding. It enables models to grasp long-term dependencies, track narratives, and maintain coherence in extended dialogues. Without it, the tapestry of meaning unravels, leaving disconnected threads. As we push the boundaries of memory, we unlock new possibilities. Imagine a language model that can summarize an entire year's worth of news or maintain a detailed multi-turn conversation across weeks. Modern LLMs are coming close to this but have a way to go. The challenges are immense, but the potential is transformative. Memory may allow models to retain the past, but intelligence is more than recollection. To create truly versatile systems, we must also expand beyond words, integrating images, audio, and other modalities. How can we build models that perceive the world as richly as humans do? The answer lies in making LLMs multimodal. To truly understand the world, models must see, hear, and process information in all its forms. This is the promise of multimodality. The ability to integrate text, images, audio, and more into a unified understanding. Imagine describing an image to someone who cannot see it. You might say, "It's a serene sunset over a calm ocean with waves gently lapping at the shore." Now imagine showing that same image alongside your description. The interplay of words and visuals creates a richer, more complete experience. This is what multimodal systems aim to achieve, to bridge the gap between language and perception. One of the early breakthroughs in this field was OpenAI's GPT-4, which combines text understanding with image recognition. It can analyze a photo, interpret its contents, and generate text-based explanations. For instance, given a picture of a cluttered desk, the model might identify objects like a laptop, coffee mug, and notepad, weaving them into a coherent description. At the core of this capability is the concept of shared embeddings. These embeddings serve as a common language for diverse data types, enabling the model to connect images, text, audio, and video in a unified representation. Think of it as plotting all forms of data on the same multidimensional graph, where similar concepts cluster together. For example, the word dog might be mapped near an image of a golden retriever and the sound of a bark. This alignment allows the model to understand that these are all facets of the same idea. For images, models process pixels and extract features like shapes, colors, and textures, which are then mapped into the shared space. For audio, the model interprets waveforms to identify sounds, tones, or speech patterns. For video, it combines frames and temporal data, capturing motion and sequence. When presented with a multimodal prompt, such as describing a video of a dog barking, the model uses shared embeddings to integrate these elements seamlessly, recognizing that the image of the dog, the bark, and the action belong to a cohesive narrative. But building these systems was far from straightforward. Early models, like GPT-3, were text-only, designed to process written language in isolation. Adding new modes required rethinking the architecture. Models like Clip and DALL-E pioneered the alignment of text and images, while advancements in audio and video processing emerged more slowly due to the complexity of these data types. Among these modes, audio and video have proven the most challenging. Audio data often lacks clear boundaries, requiring models to interpret context over time. Video adds another layer of complexity, demanding the integration of spatial and temporal information, a task that pushes the limits of computational resources. Aligning these modes into a single framework also raises practical and ethical challenges. Training multimodal models requires massive datasets, which can be resource-intensive and prone to biases. Ensuring that these systems remain fair and unbiased across all data types is an ongoing challenge for researchers. Despite these hurdles, the potential of multimodality is transformative. Picture a model that can analyze medical scans while reading patient records, or one that translates a live conversation while interpreting the speaker's gestures. These systems move us closer to creating tools that interact with the world as richly and dynamically as humans do. Yet, with great capability comes great responsibility. How do we ensure that multimodal systems remain ethical, unbiased, and secure? Training a large language model is like constructing a skyscraper, where every brick is placed by an army of specialists working around the clock. But here, the bricks are data, The mortar is mathematics, and the blueprint is a complex interplay of algorithms. Behind the curtain of AI lies a world of meticulous effort, collaboration, and sheer computational power. Let's step inside. Picture a day in an LLM research lab. The air hums with the sound of servers running simulations, while teams huddle around screens, analyzing results and tweaking parameters. On any given day, researchers debug models, experiment with hyperparameters, and brainstorm innovative tweaks. Others dive into the latest research papers, seeking inspiration for the next breakthrough. It's a highly collaborative environment where every role plays a crucial part. AI researchers design new architectures and optimize algorithms. Data scientists curate and pre-process vast data sets. Engineers manage the compute infrastructure to ensure seamless training. Ethics and policy specialists mitigate biases and ensure responsible use. And product managers bridge the gap between research and real-world applications. The backbone of this effort is computational power. Imagine a supercomputer running tens of thousands of GPUs or TPUs simultaneously. Training a model like GPT-4 requires weeks of computation, consuming the energy equivalent to powering a small city. It reportedly cost over $100 million to train. Such endeavors push the limits of what current infrastructure can achieve. The data requirements are equally staggering. Billions of words, scraped from books, articles, and the web, form the foundation. Some experts believe that there isn't enough data in the world to train a model with ambitions as high as GPT-5. This raises profound questions about the future of scaling and innovation in AI. Pre-processing this data to ensure diversity, relevance, and quality is an enormous task, involving countless iterations to refine. But breakthroughs come slowly. For every success, there are weeks of failed experiments, endless hours spent tuning a single learning rate or embedding layer. Yet, it is these small victories that collectively lead to leaps in performance. Collaboration is the key to overcoming these challenges. Multinational teams pool expertise and resources, forming partnerships with cloud providers and universities to access critical infrastructure. It's a global effort, with researchers across continents working together to push the boundaries of what's possible. Every model you interact with, every prediction it makes, is the result of thousands of hours of work, cutting-edge research, and an immense infrastructure humming quietly in the background. It's not just code or math. It's humanity's collective effort to teach machines the art of understanding. So far, we have explored the ethical challenges of training data selection, ensuring diversity, fairness, and responsibility in the datasets that shape large language models. These principles form the foundation of trust in AI. But building trust doesn't stop at the data. It extends to how we tailor models to meet specific needs. This brings us to explore how large language models evolve, from general-purpose systems to specialized tools, through fine-tuning and transfer learning. The development of fine-tuning and transfer learning represents a shift in how we approach AI training. Early models were trained from scratch, requiring immense data sets and computation to build even a basic understanding of language. This process was time-consuming and resource-intensive. The advent of pre-training changed everything. Researchers discovered that models could first learn general linguistic patterns from diverse, large-scale datasets. This phase, known as pre-training, created a foundational understanding of language. Fine-tuning then allowed these pre-trained models to specialize in specific tasks, drastically reducing the time and resources needed for training. Fine-tuning builds on the foundation laid by pre-training. It involves retraining a pre-trained model on domain-specific datasets. For example, a healthcare application might fine-tune a model using medical literature, enabling it to understand and generate content tailored to doctors and patients. Similarly, a legal assistant tool could fine-tune on case law and contracts to excel in legal analysis. This process requires balance. Fine-tuning too aggressively risks overfitting, where the model becomes overly tailored to the fine-tuning dataset and loses its ability to generalize. Techniques like low-rank adaptation, or LAW, mitigate this risk by adjusting only a subset of parameters, maintaining efficiency while enhancing task-specific performance. Transfer learning extends the principles of fine-tuning, allowing models to adapt their knowledge to new domains or tasks. Consider this. A model trained to summarize novels can apply its understanding of summarization to research papers with minimal retraining. This approach drastically reduces the data and compute required compared to starting from scratch. Transfer learning is particularly impactful in low-resource settings where data is scarce. For example, models trained in high-resource languages like English can adapt to translate or generate content in less represented languages, bridging digital divides and expanding access to AI. Both fine-tuning and transfer learning work hand in hand, enabling models to excel at specific tasks while retaining their broad capabilities. But as models get bigger, more complex, and more power, a critical question emerges. How do we align their outputs with human values and expectations? How do we ensure that these systems not only work, but work for us? This is where reinforcement learning from human feedback, or RLHF, comes into play. At its core, RLHF combines the strengths of machine learning with human insight. It's a process that ensures AI systems align their behavior with what humans find helpful, ethical, and appropriate. But how does it work? RLHF begins with a base model, a pre-trained system capable of generating a wide range of outputs. Human feedback guides this model toward better responses. Here's how. First, humans evaluate a set of model outputs, ranking them from most to least helpful or appropriate. These rankings are used to train a reward model, which acts as a proxy for human preferences. The reward model then guides the base model, teaching it to prioritize responses that align with human feedback. The process doesn't end there. The system undergoes iterative training, where its outputs are continually evaluated and refined. Over time, the model learns to balance competing demands: clarity, accuracy, creativity, and alignment with ethical standards. RLHF isn't just theoretical, it's the backbone of many practical applications. For instance, conversational AI systems like ChatGPT rely on RLHF to improve their dialogue quality. By incorporating feedback from millions of interactions, these systems learn to provide more relevant, respectful, and engaging responses. Beyond conversation, RLHF plays a critical role in applications like content moderation, where models must navigate sensitive topics, and in educational tools, where personalized feedback can enhance learning outcomes. Despite its promise, RLHF faces significant challenges. Human feedback is inherently subjective, varying across individuals and cultures. What one person finds helpful, another might find irrelevant or even offensive. Balancing these perspectives is a constant challenge for researchers. Moreover, scaling RLHF is resource-intensive. Collecting high-quality feedback from diverse groups requires time, effort, and collaboration. Yet, these challenges underscore the importance of RLHF. It's the bridge between technical capability and social responsibility. Reinforcement learning from human feedback transforms AI from a powerful tool into a trusted collaborator. While RLHF ensures models align with human values, it still relies on structured guidance. But what if models could go further, learning to solve novel problems with minimal examples or adapt on the fly? The range of scenarios that the model is exposed to is, well, limitless. This idea goes beyond alignment. It touches on the very nature of intelligence. It's the domain of meta-learning and few-shot capabilities. Reinforcement learning from human feedback ensures alignment with our values. But what about adaptability? How do we enable models to tackle entirely new problems with just a few examples, or even none at all? This is the promise of meta-learning and few-shot capabilities, an AI's ability to learn how to learn. At its heart, this is about recognizing patterns across tasks. Imagine a model that has mastered various card games. Instead of starting from scratch when introduced to a new game, it applies strategies from previous games, learning the rules with minimal guidance. This ability to generalize quickly underpins what we call meta-learning, or learning to learn. This concept extends to how models process information in real time. In-concept learning is a striking example. Rather than requiring additional training, the model uses patterns within the input prompt itself to adapt and generate appropriate responses. For instance, if a prompt provides examples of translating English to French, the model can infer the task and perform additional translations without explicit fine-tuning. This ability makes language models incredibly versatile. Few-shot learning, where the model performs well after seeing only a few examples, is a direct outcome of both meta-learning and in-context learning. Together, they transform how models handle scenarios with minimal data. Consider this in action. A language model fine-tuned in English might be tasked with translating a rare dialect. By analyzing just a handful of examples, it adapts its knowledge to perform effectively. Similarly, in medical diagnostics, a model trained on common ailments can leverage these principles to recognize rare diseases after reviewing a few case studies. This adaptability holds transformative potential across fields. The mechanics behind these capabilities rely on advanced optimization techniques. Traditional training minimizes errors for specific tasks, but meta-learning optimizes the model's ability to minimize errors across tasks. This framework accelerates learning even in unfamiliar domains. One pivotal method is the model-agnostic meta-learning algorithm, or MAL, which trains models to adapt rapidly with just a few gradient updates. Yet challenges remain. Meta-learning requires diverse data sets to ensure generalization across tasks, and while few-shot and in-context learning reduce dependency on extensive data, they demand careful design of prompts and tasks to achieve meaningful outcomes. Overcoming these hurdles is essential to unlocking the full potential of these techniques. As we push the boundaries of adaptability, few-shot and in-constant learning pave the way for democratizing AI. Imagine a world where anyone can teach an AI to solve a problem with just a handful of examples. But adaptability alone isn't enough. To truly trust these systems, we must ensure they remain interpretable, explainable, and aligned with our expectations. We need to prevent models from becoming a black box. As language models grow more adaptable, they also grow more complex. Their decisions, once traceable, now emerge from layers of mathematical abstraction. How do we make sense of their outputs? How do we trust systems that we don't fully understand? This is the challenge of interpretability and explainability. The quest to make AI transparent, accountable, and trustworthy. Imagine a doctor using an AI system to recommend treatments for a critically ill patient. The AI suggests an unconventional medication, but without an explanation, which leaves the doctor wondering, was this based on sound medical reasoning or a flaw in the system? In high-stakes situations like this, understanding the reasoning behind AI decisions isn't just helpful, it's essential. Interpretability ensures that AI systems provide insight into their reasoning, allowing users to evaluate whether the model's logic aligns with their goals and expectations. Without it, we risk deploying systems that behave unpredictably or even harmfully. Researchers employ various techniques to shed light on the inner workings of models. One common approach is attention visualization, which highlights the parts of the input text the model focused on while generating its output. For example, in translating a sentence, attention maps can show which words the model considered most relevant in each step. Another technique is feature importance analysis, which identifies the key factors influencing the model's predictions. In a sentiment analysis task, for instance, this method might reveal that words like excellent or terrible had the greatest impact on the result. Yet, interpretability is far from straightforward. Modern neural networks operate in high-dimensional spaces, making their decision processes difficult to translate into human terms. Simplifying these processes for explanation risks losing critical nuances, while overly detailed explanations can overwhelm users with complexity. Then the model needs explainability. This goes beyond interpretability by focusing on communication. It's not just about understanding the model internally, but explaining its behavior to diverse audiences. For policymakers, this might mean demonstrating fairness and compliance. For developers, it could mean debugging and optimization. For end users, it's about building trust. Explainable AI ensures that everyone, from experts to lay people, can engage with and benefit from these systems. Throughout history, humanity has achieved feats that reshaped civilization. The pyramids of Egypt, standing for thousands of years, showcased our mastery of engineering and resourcefulness. The Hoover Dam harnessed the untamed power of rivers, providing life and industry to millions. The Apollo missions took us beyond Earth, planting our footsteps on the moon, and the splitting of the atom unlocked a source of energy and responsibility that changed the course of history. Each of these achievements was a reflection of vision, courage, and an unparalleled commitment to pushing the boundaries of what was possible. Today, the development of large language models joins these ranks of transformative milestones. With trillions of parameters, petabytes of data, and supercomputers running continuously for weeks, the creation of these models is a marvel of modern engineering. They're not just algorithms, they're systems capable of understanding and generating human language, with implications that stretch across every facet of life. But this is just the beginning. The advancing techniques for LLM development hold untold potential. Federated learning, a paradigm that distributes training across multiple nodes without centralizing data, promises to democratize model development while addressing privacy concerns. Sparse expert models could revolutionize efficiency, activating only the most relevant parts of a neural network for each task. These approaches may make models more sustainable and scalable, bringing them closer to the hands of every researcher, developer, and creator. Imagine an AI capable of real-time, self-guided learning. Google's recent advancements in synthetic training data point to models that can generate and refine their own knowledge. Such capabilities could allow future systems to bridge the gaps in their own understanding, creating a feedback loop of continuous improvement. And then there are multimodal systems, models that integrate text, images, video, and audio seamlessly. These systems are already emerging, with tools like OpenAI's GPT-4 and Google's Gemini leading the way. Imagine a system that could design a bridge by analyzing architectural blueprints, reading technical documentation, and simulating environmental impacts all at once. The possibilities are limited only by our imagination. Yet, as we stand on the precipice of these advancements, we must also confront profound challenges. The ethical questions loom large. How do we ensure that these systems remain safe, unbiased, and aligned with human values? Can they be made interpretable enough to trust in high-stakes scenarios like medicine or justice? And as they grow more capable, could they reveal patterns and insights that surpass human understanding, forcing us to rethink our own role in shaping the world? Like the explorers, engineers, and visionaries before us, we are venturing into uncharted territory. The breakthroughs in computer science and engineering that brought us here are the foundation. But the future of AI is as vast and mysterious as the cosmos. As we look ahead, we are reminded of one universal truth: every leap forward is built on the shoulders of giants. The foundations of foundational models tell a story of perseverance and vision. Where we take them from here is constrained only by the boundaries of our imagination.